You know, we spend so much of our lives online, but have you ever really stopped to think about the physical stuff that makes it all happen? Today, we're going to pull back the curtain and look at the actual wires, the unseen, unsung heroes that power our entire digital world.
I mean, really think about it for a second. You take this little plastic plug, you click it into your computer, and bam, the entire planet's worth of information is right there. How on earth does that actually work? It seriously feels like magic, but it's really a story about some incredibly clever engineering.
Okay, so our journey starts right here with this familiar little plastic connector. You've probably plugged one of these in 1,000 times without a second thought. Its official name is an RJ45, and for most of us using a wired connection, this is the literal front door to the internet.
And that little click you hear when you plug it in, that's more than just plastic locking into place. It's like a handshake, an agreement. That cable and that port are both part of a huge system called Ethernet, which is basically the invisible hero that makes our networks actually, well, work.
And here's the key thing to get. Ethernet isn't one single thing you can buy. It's more like a shared language. It's a giant universal rulebook that makes sure a cable from, say, brand A can talk to a router from brand B, which can then talk to a laptop from brand C. Without these rules, it'd be total chaos. Nothing would connect.
So, what do these rules of the road actually do? Well, they solve a really fundamental problem, making sure that when one gadget starts talking, another one can actually understand what it's saying.
The best way to think about it is like this. If I speak English and you only speak Japanese, we can't communicate, right? It's exactly the same with your computer and your router. Without a shared standard, a common language for sending and receiving signals, all that data is just meaningless electrical noise on the wire.
So at the very, very bottom of all this, it all comes down to one thing, the bit. Just think of it as a tiny electrical pulse. It's either on or off, a 1 or a 0. That's it. That is the entire alphabet of digital communication. But when you string 8 of those little bits together, you get 1 byte. And that's enough information to represent something useful like a single letter of the alphabet.
From there, it's all about speed. How many of these ones and zeros can we shove down the wire every second? Let's start small. 1,000 bits per second gives you 1 kilobit per second, or kbps. And believe it or not, back in the dial-up days, this felt blazing fast. But of course, technology never sits still. Pretty soon we were sending 1,000,000 bits every second. That's 1 megabit, or Mbps. Now we're getting into speeds that most of us recognize from early broadband internet.
And that brings us to today's gold standard for a fast home or office network, the gigabit. We're not talking 1,000,000 anymore. We're talking 1 billion individual on or off electrical pulses firing down that copper wire every single second. The scale is just staggering.
Okay, so we've got this fire hose of ones and zeros. But wait a minute, this creates a new problem. How can a computer send and receive data at the same time on the same cable without it all just smashing together into a garbled mess? Well, the solution is actually hidden inside the cable itself. So if you were to slice open a typical Ethernet cable, you wouldn't find just one wire. You'd find 8 of them, all twisted together into 4 pairs. And this design isn't just for show. It's called unshielded twisted pair, or UTP, and twisting the wires together is absolutely crucial for canceling out electrical interference that could mess up the signal.
So here's how those pairs are used so cleverly. When you connect 2 different kinds of devices, like your PC to a network switch, you use what's called a straight-through cable. See, your PC is designed to transmit, to talk, on one pair of wires, and the switch is designed to receive, to listen, on that exact same pair. It works perfectly because they have opposite jobs. But what happens if you try to connect 2 similar devices, like 2 switches together? Now you've got a problem. They both want to talk on the same set of wires, and they're both trying to listen on the other set. It's like 2 people talking at once with nobody listening. The old school fix was a special crossover cable. It literally crosses the wires inside, so the transmit wires from one switch connect to the receive wires on the other. A simple physical solution.
Now, if you're thinking, wait a second, I've never had to think about which cable to use, you're absolutely right. And that's because modern gear is so much smarter. Pretty much every device today has this brilliant feature called Auto MDX. The port can actually sense what it's connected to and will automatically cross over the pins internally if it needs to. It's a perfect example of great engineering just making our lives easier.
So copper is the absolute workhorse for our local networks. It's everywhere, but it has one big fatal flaw.
a hard physical limit that forced us to find a completely new way of sending information. And here it is. That fatal flaw is distance. An electrical signal running down a copper wire can only go about 100 meters, roughly the length of a football field, before the signal just fades into noise. That's totally fine for wiring up an office, sure, but how do you connect two buildings? How do you connect two cities? You need something else entirely.
And the solution was just genius. Stop using electricity and start using light. This is fiber optics. Instead of pushing electrons through a copper wire, we're now flashing tiny pulses of light down a strand of pure glass that's thinner than a human hair. Moving from electricity to light completely changed the game.
And there are basically two main flavors of fiber. You've got multimode, which you can think of kind of like a flashlight. It uses a simpler, less focused light source, which is great for shorter distances, like connecting buildings on a big campus. But for the really long haul, you need single-mode fiber. This uses a hyper-focused, powerful laser beam, allowing a signal to travel for dozens, even hundreds of kilometers with almost zero loss. This is the stuff that forms the backbone of the internet, running under the oceans to link entire continents.
So, which one is better, old-school copper or new-school fiber? Well, the truth is, it's not really a competition. It's all about using the right tool for the right job.
Let's break it down. Copper is way cheaper and a lot easier to work with, which makes it perfect for that final stretch of cable running to your desk. But fiber is the undisputed king of distance and speed. It's not even close. Plus, since it's just light, it's totally immune to electrical interference. And it's much more secure because it doesn't leak any signal you could eavesdrop on. They're not competitors, they're partners.
So, the next time you click that network cable into place, just take a second to picture that incredible journey your signal is about to take, from electricity in your room to pulses of light under an ocean and back again in the blink of an eye. And it really leaves us with a huge question for the future. As our hunger for data and speed just keeps growing, is it only a matter of time before these tiny strands of glass replace copper for good, bringing the speed of light literally right to our fingertips? Thanks for joining us.